Okay, welcome to our distinguished lecture series. I'm very delighted and privileged to introduce our distinguished speaker today, Dr. Sriram, who is an amazing colleague and friend for over several decades, who is doing very exciting work at the National Institute of Science and Technology. He's there serving as the Chief of Software and System Division, which one of the prime divisions in their laboratory of information technology. I had the privilege to work there many years ago in the same building, I believe, where Ram is now, and it's a great place, house of many Nobel Prize laureates, and he'll be sharing with us today his work on transforming healthcare through artificial intelligence solutions. He has an extensive biography, so I'll save the time. You can read it. But once you hear from Ram, you'll realize the power and exactly what he's working on and what he brings to the table from the research perspective. Welcome again to Miami.
Thank you very much, Elena, for giving this opportunity. And I have actually not given this a talk in person for almost 2 years. So it's nice to open this my talking circuit along with the University of Miami, and I'm going to go to other places later on. But this is the first after 2 years. And also it's kind of interesting because this allowed me to think a lot about various subjects too, and how life is progressing. And AI is something which I started about 4 decades ago in 1980 with 2 people, Professor Stephen J. Fenves and Professor Raj Reddy. For those of you who may not know Steve Fenves, he's the guy who wrote the first analysis program on a digital computer in 1960. Okay, for anyone who does anything to do with finite element analysis, or anyone who has done the design of this building, it goes to Steve Fenves. And then he got interested in AI, and then there was Professor Raj Reddy, who is a speech processing person. And in fact, any speech understanding recognition system that you kind of buy nowadays in the market can be traced to Raj Reddy's lab. So I had the distinct pleasure of working under these 2 stalwarts in 1980. So after that, I went to MIT and taught, and I've been working in this area for all this entire revolutions that you're going to see. So what I'm going to do today is to go through kind of very fast through my slides, and this set of slides are available. And I think Elena, you can give it to whoever is interested, or if you send me email. Pardon? I don't know, wherever it is posted, you can do whatever you want to do with it. Okay. So what I don't know how much background people, a lot of you actually have all this background in AI. But however, I didn't really know about that when I made this talk. So I'm going to talk about a little brief history of AI. Then I'll talk a little bit about the National Institute of Standards and Technology and its role in AI. As some of you are aware of, Nist is going to play an increasingly important role in artificial intelligence. Then I've been working in healthcare for the last 2 decades or so, and I'll talk about healthcare and how AI can be applied to healthcare. I'll talk about 3 revolutions. It could be waves or revolutions depending on how you look at it. The first wave, the second wave, and the third wave. And then I'll talk about the future and some summarizing, I think. So now in terms of intelligence, I don't want to go too much into detail on that, but you can all see people always talk about intelligence. What is kind of intelligence? So some people kind of talk about the goal-directed view of intelligence and so on. Okay, so I mean, there's a difference on whom you talk to. Everyone gives definitions of this intelligence. And people, you have pets here, they kind of think that dogs or cats are very intelligent too. So now we can see that's actually they are in a way, depending on what do you think the various attributes of intelligent things. And this is normally what we think they are, because we say that, well, they are mental attitudes. You can perceive and model the external worlds, like all you are looking at here and making. And what you're doing is, as I'm talking, you're creating some knowledge structures in your brain, relationships, and how these things are connected to and things like that. So you're making that in your thing. And then you're able to, understanding is another thing which is very interesting, because a lot of times this is also have some semantics associated with it. And in fact, actually, there's an interesting joke about this notion of understanding, whereas a lady goes to the doctor and she can't hear or something like that. Okay, so then after some time, it could be either way, a woman or man, depending on how you look at it. And after some time, the doctor gives this very innovative procedure for getting her hearing properly. So then she goes back to the thing, and after 10, 15 days comes back and says, doctor, I have a problem. Doctor says, what's the problem? Don't you hear anything? She says, well, I hear everything my husband says, but I don't understand a thing. Okay. So this is the notion of understanding. Now we can think about semantics of understanding. What do you mean by understanding? When people say natural language understanding, what do you mean by that? Okay. Anyway, so the other thing is that notion of innovative, solving problems in an innovative manner. And there's a wide spectrum of these things. We can talk forever. And one of the things human beings do very well is they generalize things. And I guess this is a data institute. And you deal with tons and tons of data all the time. And what are you doing with data? You're filing abstractions, generalizations. So even a lot of data is coming from traffic here, there, and Waze does that all the time. And then you kind of have some patterns and you generalize that to a higher level. So the planning and predicting natural language, using language, all these things are important. But then Gardner came up with this very good book called Theory of Multiple Intelligences. And the idea is that intelligence is not only at this particular level. There are other things to do with intelligence, like awareness, consciousness, aesthetic appreciation, emotion, muscular coordination, sensory acuteness. All these things are also part of this intelligence thing. So when people talk about artificial intelligence, they really have to talk about all of them in a holistic sense and not at a single dimension of some qualitative or quantitative intelligence. And Howard Gardner, even the musicians, for example, that's the intelligence kind of thing. So it's in one direction, in this multidimensional view of intelligence, that's one direction of the intelligence. So if your kid, for example, I always tell people, if your son or daughter is not really, you don't think they're doing all this studies to become a medical doctor or a lawyer or an engineer, don't worry about it, because they may have some other piece of intelligence that they may be able to pursue, like artistic intelligence and so on. So when you talk about computers, also then people came up with this thing, well, let's see what can we do with computers. So this is a very old definition with Ellen Rich did it in 1980s in her book. So you have two things around here. You have an intelligent agent like us, or a robot moving around, and there's the environment. So the intelligent agent is interacting with the environment through several ways. One is perception. That is, you are receiving all this information, big data is coming in. Like, imagine when you're driving, for example, how much data that you're getting into your brain coming from all directions. But however, what do? A lot of unnecessary information you throw away. Even though your sensors are getting all that information, that's the time the intelligent agent is thinking about it, and based on the thinking process, does some actions. And the actions are done either basically software, or you can have manipulators. We're talking about a robot, or you're talking about Tesla car, or one of these things, the automated driving cars. You really, they're doing manipulators which are going around. So then let's briefly talk about the evolution of AI. I kind of divide this into various stages. First, I call it as the prehistory. And that is in terms, if you look at the prehistory of AI, there is the Paleolithic time when you have the Indian and the Greek philosophers. They did a lot of thinking in this process. In fact, it's kind of interesting if you go into the Indian philosophy of the Vedas and those kinds of things, which some of you may or may not be familiar with. They talk about ontologies, they talk about relationships, they talk about inference, they talk about analogy, they talk about a whole lot of stuff in the old Indian philosophy. I'm not talking about the religion, I'm talking about the philosophy around here, if you look at the philosophy. And some of the philosophies talk about the abstractions and those sort of things. Like, for example, if I ask you a question, what is that there? Okay. Now, that is a notion as an object, okay? It's a transient object which exists, and tomorrow it may not exist at all. So these kinds of things that talk about a transient object, existence of the objects. And the notion of ontology came into being because of they're trying to define what is the notion of being. What is a being? What is the existence? And that now ontological engineering has become a big field right now. And then later on, in the Neolithic period, Hume, Russell, Turing, and a whole lot of people came up with this notion of symbolic reasoning and things. But in terms of the AI word was coined, as you all know, in 1956 at Dartmouth College, when McCarthy and other people were there, Minsky, McCarthy, on these people were there, and this word was coined at that stage. But then in the first wave, before the first wave, we also saw the early years and the rise of knowledge systems. Like, for example, this went on from 1957, the year I was born, to about 1980, the year I came to CMU. There was things like, we came to United States. There were things like general problem solver, Dendral, hearsay, maxima. Hearsay is the one which Raj Reddy came up with. Mycin was the medical system. And there's Sidlu, Shaky, robotics systems, they were all there. So then, of course, in the 1980s, this whole notion came into picture that knowledge is power. So what you do is people said that you build these knowledge-based systems or expert systems, you build this enormous amount of knowledge in the computer, and then you can solve a wide range of problems. There are a lot of problems with human beings solve, and you can solve all these things. And Edward Feigenbaum is one of the people who kind of believed that this is going to revolutionize and everything, knowledge-based expert systems are going to take over the world. And at the time in 1980s, if you are in the knowledge-based expert system, if you had graduated with that, you would get huge salaries also, $100,000. I mean, this is a lot of money in 1980s. They used to get that kind of a money, I think. But then what happened? Something happened after that. I mean, there was a lot of interest, a lot of enthusiasm, a lot of companies were formed, a lot of knowledge-based companies were formed, and so on. But that kind of enthusiasm kind of somehow or other went off, because what happened is that soon you can build all these knowledge structures. There are some fundamental problems with that. One is creating those knowledge structures is not very easy, because you have to mine and mold the knowledge from experts, and getting knowledge out of experts is not very easy. Okay, because first of all, they don't want to give the knowledge, and secondly, they'll talk about all kinds of things. And we had experience in that. We built a knowledge-based expert system for the Atlanta People Mover, where this was in 1986. Whenever you go to the airport, and you go into those trains, and they're all completely automatic. And Westinghouse had built those systems in the early, 70s or something like that. And in Atlanta airport, that mover had a problem. The doors used to open up, and the doors never used to close and things like that. So they thought it was a transportation problem, and we were in civil engineering, and they handed it over to us. But it has nothing to do with civil engineering. It's a whole lot of things about how the circuits work, and you have the chips interacting with one another, and so on and so forth. So we invented actually something called hierarchical diagnosis at that time, but unfortunately we couldn't publish because we had this contract with Westinghouse. We can. But then what happened is, after we gotten all the knowledge and built this massive expert system, the president of the organization talked to us and said, "Can you, this is pretty interesting, except there's one other problem we had. Our systems were running in Pittsburgh, but the demonstration was in Atlanta. And, at the time, we had only 32-bit, whatever it is, memory was 32 megabytes or something like that, total memory on the system, which was shared. It was really slow. It will take forever, I think, by the time the accidents would happen or whatever it is. But anyway, he said, this is all well and good, but here is what I'll do. I'll put in a lot of money into this. Next year, I want a working system, a completely functional system. But you can't do that, because at that time, the systems were not fast enough, number one. And number two, all this knowledge that you have to get from people was not very easy to get in and put the thing together. Anyway, so that was the story. And it happened to other systems too. And these things were breaking. And people didn't know what to do, because if it didn't have an answer, and it broke. And then what we saw, and there is this thing called the silent period. And what has happened around in the silent period from 1990 to 2000 is there's a lot of stuff. The chess system called Deep Blue came in, the rise of the robots, when the robots went to Mars and things like that. This commercialization was AI was happening, especially for speech recognition. In fact, I don't know how many of you know this nuances system, naturally speaking, Dragon, that came out of Raj Reddy's lab, Jim and Janet Baker, husband-wife team. Jim was Raj Reddy's student, and they went ahead and built this thing. But this is based on a Markov's model, not on a traditional symbolic systems. So now hearsay was more in symbolic, and this is more probabilistic in nature. But it was very successful. So the commercialization was happening. Then suddenly these neural networks came into the fore. We call it as a second wave or the second revolution. And what the neural networks did very well, and the reason neural networks were very successful, and in fact, the interesting thing is that Jeffrey Hinton was at Carnegie Mellon when I was there as a graduate student, and he was talking about neural networks, and no one took him seriously, to tell the truth. Okay. Oh, yeah, these are fine. We all were talking about, it's interesting. It's obvious, how the brain is wired towards with all these neurons and things like that. That was an obvious thing. But neural networks actually did something. It was predicated on the fact that it's an optimization kind of gradient optimization kind of problem. That's what it was doing. So if you look at it carefully, the neural networks, and you take the forward and the backward propagation, it's really optimization kind of thing. You're finding the delta function, you're minimizing that thing, and that's what you're doing as such. Except that there were only about 4 layers at most around that time, the thing. And they were very computationally very expensive, okay, because you have to build these networks, and then you have to train these networks and so on. So initially they had problems, but then something happened. That is, the computers were becoming extremely fast, and your GPUs, CPUs, parallel processing, and all those things happened. So these systems also, you can build massive systems. And imagine building, if you have all these huge zillions of networks of nodes, and you throw data into this, you will get something out of it, okay? So that was what was happening. And the thing is that these systems are extremely good at recognizing faces. We'll come to that later on the thing. So that's what happened. Then, of course, now what you are seeing is that we are what is known as the third wave, which is a symbiosis of neural networks and knowledge networks, and I'll come to that briefly. And finally, people ask me, is there a fourth wave? Yeah, there is a fourth wave. And the tsunami is coming. And the fourth wave is more to do with human being and the consciousness. It's artificial you. There is something called consciousness, and then we go into philosophy. And I'm not going to talk about fourth wave. Okay. So there's another interesting talk here, which is Henry Kotz's talk at that URL. You can click on that and in the slides when you get it. And also he wrote a paper recently, which came out in AI magazine this year, this spring. So our spring or whatever. Yeah, it came out recently. Very beautifully, he said, he gave the history of this thing. Henry Kotz, by the way, is at NSF right now. So in terms of Nist, the main mission of Nist is to promote innovation in industrial competitiveness in United States. And we are key things there are advancing measurement science, standards, and technology, and in a ways that enhance the economic security of things. And so some of you have interacted with Elena is to interact with us quite a lot. In fact, Akko was in my division for a long time, and I still associated with it, I guess. So in terms of AI and Nist, there are two things that we focus on. One is artificial intelligence for Nist and Nist for AI. And the idea is that we are a measurement lab. In fact, all the standard units of measurement, Nist kind of maintains it. And most of them are, except kilogram, which is physical still, most of them are based on the electromagnetic radiation and those kinds of concepts. E equals mc squared is what now people are looking into. And by Planck's constant, they want to make the mass also a virtual kind of thing, okay, not a physical system. So we do a lot of measurements kind of thing. So the issue is AI for Nist means how can you use artificial intelligence to help make better measurements? As Elena mentioned, we got a number of Nobel Prizes, and most of them were done because of the physics people. They were trying to understand the notion of time. And for that, they were trying to take these atoms and make it slower and slower and slower. And to do that, you need to go into all kinds of things like the Einstein-Bose condensate and those kinds of things, and got Nobel Prizes for that. So that's in the measurement area in the time domain. So we want to see how we can help these people by using AI. And then there is a notion of Nist for AI. So that means this artificial intelligence now is becoming very popular in various areas. How can you measure AI is the question. How can you use AI to measure things, to help measure things, but also you need to measure AI. Okay. Example of that, like there are a number of trustworthy AI is an interesting thing. How do you trust your AI system? Let us say you are a doctor and you want to you make a diagnosis. How do you trust that this system actually, how do you believe this system? And then there are a number of applications like robotics, material science, smart manufacturing, biomedical imaging. These are all the applications that we do in Nist. So in the Nist AI program, if you go to the Nist site, there are several things that we focus on. One is conducting foundational research to advance trustworthy AI is the key thing. And then we want to develop this established benchmark and develop metrics to evaluate AI techniques. So that's measuring AI. One is we use, again, as I said, fundamental foundational research we do. Then we use AI for measurement techniques. So we establish benchmarks and develop metrics to evaluate AI. Now, this is another interesting problem. That is, like when you're talking about big data and you're talking about data science, how do you authenticate this data? And can you develop data sets so people can test your algorithms? So that, and then Nist can be a way where you can have these data sets and people can use those standard data sets so they can test their algorithms and towards the trustworthiness and things. So there are a number of things that we do. We have been working in the past on aspects of AI. I don't want to go too much of it. There's a track program that we do evaluating search techniques. And then the DARPA speech system also, we had this speech corpus thing. So the number of ways of interacting with Nist, we have guest researchers and faculty associates who work with us. Grants and contracts are one way of doing it. IPA, interpersonal agency, I think that's how Haka was involved in there. I don't know, but Elena, you are also probably in the IPA mechanism to work with
No,
Nist.
no, no,
Yeah.
actually, I was fed.
Yeah. Okay. So there are some students. Yeah. There are some students who come and work with us. We have a Nist postdoctoral program, and that's one of the things I want to see. If you have potential citizens, US citizens, would like to kind of join our program. There's a lot of advantages working at Nist. Anyway, so let me go to healthcare now. And healthcare is an interesting thing. In the United States, we spend about $4.1 trillion on healthcare in 2020. Now, 4 trillion, 2 trillion, $1 trillion is more than the GDP of India, which is one of the largest, whose population is probably second largest in the world, or maybe one soon. So there are 1.2 billion people out there, and they spend their GDP is about $3 trillion. And the United States spend more money on healthcare, I think. And in this case, it's about 750 billion is lost due to inefficiencies in the system. So, and that's the reason why AI can play a major role in these things. So within healthcare is a huge thing. There's various levels of biological information if you look at it. So you can go from the top level ecologies to all the level to the bottom level, which is DNA. Now, why is this important? It's important because there are different levels of abstraction around here. Now, when you go to a doctor, when the doctor does some diagnosis and things like that, that particular doctor is working at the individual level. And then when you're talking about COVID-19 and how it's spread across the population, we're talking about the population level of how to deal with COVID kind of thing. And then you use AI techniques to manage COVID, the spread of the COVID pandemic. Then you have the organs level, tissues, you have the cells, and finally we go into DNA part of it. So the healthcare aspects of the work that we do is around that level, like individuals, organs, and tissues. And then we also work on biosciences. You know, when the people talk about biological sciences and bioinformatics, they're talking about this particular level. And there's a lot of things you can do both from an informational technology point of view in each one of them because it plays a major role. Like, for example, we do protein-protein interaction problems. Like, for example, Alzheimer's is a disease which can affect a lot of us right now and maybe in the future. And at Nist, we have worked on that, and we have developed, actually, there's some pathways were discovered by NIH people, and they discovered the pathways of in vitro, and we actually did the in silico experiments of that. So here is the interesting part, and you guys actually have a good opportunity to do that. And the reason is that you have a medical school around here. So when you have a medical school, the medical school folks are doing a lot of in vitro and in vivo kind of experiments. But what you can do is in silico kind of thing, and you can model the systems. They require large resources. That's a different issue. And AI and those kinds of things can predict what is the binding mechanisms. Even like for example, in COVID, you have the binding happens when the virus comes in and attaches to the cell. There is a binding mechanism that happens. And depending on where exactly it binds, all kinds of things can happen in the thing. And some people were more resistant to the COVID when it came out. And the reason is that they had some mutations where this binding didn't happen properly. And so this is a whole different story. I don't know. Right. So you can go from now, then in terms of the fields that has happened is in terms of one of the revolutions that has happened is a genomic revolution. So you can go from the genomics to proteomics to metabolites to the cellular level to the organism behavior. So there's a whole pathway around here that you go. And again, depending on what you're doing, you can go to genomics and work on that. You can go at the phenotype level and work on the human beings. And the other thing that has happened here is that you also have the convergence of different fields coming into the picture, like of the genomics, you have the biological analysis, and then you have computer science, AI, and so on, and engineering. All of them are merging into this thing called system biology or systems medicine. And that is the future. And if you look at the future of medicine, if you're talking about advances making the future health vision attainable, there are three things that are happening here. One is the advances in healthcare technology, like the Human Genome Project, pharmaceutical and nutraceutical, medical devices. There are lots and lots of major advances are happening. And in fact, you can go to a medical people and they'll tell you what's happening. And the second thing that's happening is that advances in healthcare practice. This is the practice of healthcare, where you're managing diseases, evidence-based healthcare, continuum of care. And there's something which, again, interesting happening is called the mind-body medicine. So the human being, for example, is actually three-dimensional. You cannot view person like just only the pathology of the disease, but it's really three dimensions. One is the pathology of the disease is in one direction. And the second direction is the social aspects of this whole thing. Okay. And why do people go to church? When people die, Why do lots of people come and talk to them? That's a social aspect of this thing. Okay, that is one thing. And the third thing, which is it's not physiological and more psychological in nature, is things like meditation. So when you do meditation, actually you can reduce a lot of problems. And if you look at people who have high blood pressure, for things, if you look at the pathways, the pathological pathway, you can see like there is a pituitary gland, hypothalamus, pituitary gland, and adrenal gland. There is a pathway in that. So that sends a hypothalamus sends a message, the pituitary gland sends a message to the adrenal gland, which produces corticosteroids, and that creates all kinds of problems. So that's why it creates cancer, it creates stress, blood pressure, and all those things. Now you can mitigate that. That's why when people do meditation, even though you have all kinds of problems, this is reduced. So that's one other pathway that you have to go by. The pure meditation and how it happens is a different story. There are all kinds of theories, but I can give you my theory. But then there's again the social things, and even in the stress situations, we all meet together. And that's why Zoom things don't work. It kind of works, but it's a good thing to have physical meetings and things like that. So we are meeting together. So, and how do you do all this? So this is another path that is going on. So, and then in the computing technologies, AI, networking, communications, and imaging, and this neat thing called mobile personal computing devices. Actually, I do more than phones, all kinds of things in there. So these are the kinds of things that are happening. And AI has got an interesting thing in all these things, as we will see soon. Okay. So we came up with this notion called the P9 concept. Okay. Leroy Hood, I don't know, some of you who are working in this field know who Leroy Hood is. He's a famous man in the bioinformatics area, and he actually should have gotten a Nobel Prize for what we did on the immune system, but Tony Gawa got it for that thing. That's how the immune system is. Again, I can give a lecture on immune system later on, but it's a different story. That is, it's a very interesting engineering design problem. For those of you working in engineering design, how the immune system works, you should relate that. Now, one of the things I like to do is that I like to go from different disciplines. I like to take the concepts from engineering and apply to medicine, take the concept from medicine and apply to engineering. So you learn a lot from this diverse area. So that's one of the things that is needed. And hopefully here that can happen between computer scientists, the medical personnel in healthcare, and so on. So you need that kind of thing. So this P9 concept that we came up is that medicine in the future is going to be personalized for each individual. It's going to be predictive. You can see what's going to happen. Participatory, people can participate in this whole things. In the medicine part, it should be precise. When you gave your recommendations, what went wrong, and you can do decision analytics to be very precise. It has to be preventive. Before you get diabetes, you know that you're going to get diabetes, so you prevent the thing. It has to be pervasive, point of care. So if I am sick right now, the care has to happen. It is happening during this pandemic in some sense, where people are doing telemedicine and things like that. And pervasive, that is at the point of care, is very, very important. That's what is going to be in the future. And you can see all kinds of devices. I give a whole different talk on how this P9 medicine can be implemented with. Then you have things like privacy, protectiveness in terms of security, and priced reasonably. So this is a health IT network, and I'm going to skip through the slides a little bit. You can see them in the different levels of healthcare, because healthcare happens at several levels, at the doctor's level, the point of care level, and then you have the hospitals and your network of hospitals. There's different levels of abstraction. This health level is happening. So what you see right now is electronic health records. When you go into a hospital or a doctor, they're going to record the information that your history and physical and those kinds of things. So there are a number of issues around here in terms of inputting, storing, manipulating, exchanging information, and the security aspects of it. Now, again, if you look at it carefully around here, if you're talking about manipulation, there you are doing searching for knowledge, you're mining knowledge, you're creating knowledge structures. You're talking about knowledge representation. So AI has got a big role to play around here. And even information exchange, AI has got a big role in there. Again, I give a small anecdote in that thing. It's like my sister-in-law is a rheumatologist, and she, the guy, rheumatologist is a person, what had knees and things like that, if you have pains in the bones. So there's a person who came and she gave medicine to the guy, and he went there, got the prescription. 1 week later, he came back and she asked him, "How are you doing?" He said, "My pain didn't go, but what happened is I'm feeling very happy about the whole thing." So she said, "What did you get?" So what happened is that she gave a prescription for what is known as Celebrex for arthritis. but her handwriting, the pharmacy guy read it as Celexa, which is for Prozac-like disease, the thing, for depression and things like that. So I was feeling very happy about the whole thing. So these kinds of mistakes happen all the time when information exchange between doctors also, their interpretation is that requires some knowledge structures. Okay, anyway, so there's several dimensions in terms of, I'm going to talk about now dimensions of where you can use health AI. For dimension number one is, I call it derivation formation spectrum. And in this case, what happens is you have what are known as the derivation type of problems and you have a formation type of problems. What are they? So in the derivation type of problems are things like diagnosis, where what happens in this case is that you go from a particular symptom and then you map it into some diagnosis. Okay, so it's from input to some goals you have, and then you map into that kind of thing. And diagnosis, whether it's a car diagnosis, your car fails or your body fails, diagnosis and everything. And then control is also interpretation is one part of it. Like ECG, for example, you take an ECG signal, you got to interpret what that ECG signal is. Diagnosis may be part of this interpretation, but interpretation is a task. Then you go to the other end of the spectrum where you have things like planning, scheduling, design. For example, in the medical field, you actually design experiments for the oncology, for suppose someone is suffering from cancer. So you're going to design that particular experiment. So a lot of designs, in fact, you design the hospital facility, you design a lot of things in the healthcare field. So design is, and each problem has a different way of solutions to the thing. And there's the other dimension where you can look at it is, while you're looking at this dimension of the diagnosis to design problems, the other dimension you look at is from the life cycle, starting from the embryo level to the time you die, okay? And that could be called the womb to tomb, womb to tomb, like you're born to, and then you die, okay? And then you die. Pardon?
I said diapers to defense.
Yeah, diapers to order. Yeah, so that's right, yeah. So, and then AI can be applied, and each of the things that I talked about, those kinds of that dimension, and you can have one dimension of several other dimensions. I'm thinking about other dimensions right now. So these are the two dimensions I'm showing right now, where you have the life cycle dimension, and then you have the problems type of dimension, and then you have other dimensions like building and all kinds of things which are going on in the medical field. Medical field is, as you know, that it's a $4 trillion industry. There are other things which happen out there. So let's talk about the first cycle, first wave, which is where the knowledge-based expert systems are. And this is where the model of the knowledge-based expert system, where you have the context of the short-term memory, you have a knowledge base, and the inference mechanism is happening there. It's called the thinking process. And you have these techniques like backward chaining, forward chaining, constraint propagation, hierarchical generate and tester. And then you add some explanation facility that's very important because people always talk about this AI nowadays and say, can it explain even neural networks and so on. So here is some early history of AI in medicine, and there's a book called Artificial Intelligence in Medicine, which you can go to the web and get it. This particular book has got all the important milestones that has happened in the 1980s. There was this thing by Casnet by expert at Rutgers University, which used the representation of causal networks, and glaucoma was the theme there. And mycin and emycin, which was the one which became very famous, was developed at Stanford University, started in 1975 by Ted Shortliff and people, and then it was a rule-based system. It was only addressed the infectious diseases. Then MIT had this system called ANA and other things. And then also University of Pittsburgh, there was this thing called Internist and Caduceus, which was a very, very comprehensive system. And that actually used the notion of ontologies, networks, and things like that very well. I think Popov was the person who was involved in that thing. So you can go to that. So mycin, there's a book which came out of the mycin, Edward Shortliff did. And I don't know how well you can see that thing, but it asked a number of questions about that particular person. And then came to a conclusion what kind of a disease or infection that particular has. And what mycin did, its representation was purely rule-based, no objects, well, they call it some objects, but it really rule-based system. And its object attribute values were there. And then generally there were rules like saying that if, like for example, if A, B, and C, then D kind of thing. And then what it did is it essentially did backward chaining. So that means it went from D. Like in this case, if they would want to find out whether this is strong suggestive evidence that the class of organism is Enterobacteria, something like that. For that, it has to first prove that the identity of the organism is not known with certainty, and the stain of the organism is gram-negative, the morphology of the organism is rod, and the aerobicity of the organism is aerobic. So then it has to prove each one of those statements. And you always seen that all the time. It's called deduction. Goes from the back, goal-driven kind of reasoning. That's what this one did. But one of the things that Mycin did was, because it's a rule-based, because the networks were there, it could do what is known as explanation. If someone may ask some question, and if somebody asks the question, is hospital the patient's illness with organism 1 is hospital inquired, and the guy can say, ask why, and it'll give a reason for that. And what it does is essentially go through this inference network that it has created and go down the tree. And we have developed these things in the 1980s and so on. So it can ask why, how, and those kinds of questions. So here, like, for example, how do you decide that an organism might be this particular thing, Pseudomonas? So it says that, this is the reason, and these are the rules which are involved in this, and these are the rules which fired, and that's why I make the decision. And this is explanation-based AI at the time. And it's easy to do in these rule-based frameworks. Okay. Now comes the second wave. Okay, so this is what people typically draw the thing. They talk about artificial intelligence as a whole, and then you have these things called machine learning and knowledge-based systems also. I put it like that because there is an overlap around here. And machine learning, people somehow confused with purely neural networks kind of thing. It's not true, because neural networks are only part of it. And then as neural networks became bigger and bigger, you have this notion called deep learning. So that's the one which is very popular nowadays. And if you look at the different kinds of machine models, and some of the machine models are like regression models, decision tree models, and mixture models. Now, people who are working in statistics and so on, they do a lot of things on the top. So there's a statistical AI kind of thing. Then you kind of came up with this whole notion of neural network, where you have this multi-layer perceptron models, and you have this convolutional neural networks where you kind of take the huge neural network, focus on certain features, and you, again, those features. So to manage these neural networks, so again, small features, and those features can go into things like whether the guy has a disease state 1 or disease state diabetes, retinopathy, and those kinds of things. You can get there. Okay, so that was the second wave, and the neural networks became very, very popular and so on. So you can do certain things, interesting things around here, and we did too. And there's a lot of work which is going, and these neural networks are extremely good at medical imaging kind of tasks. Because there's a lot of this data, there's output, for sure what's going to happen. And then the doctors can come in and they can tell you some regions of interest and things like that. And machines can learn automatically. So a number of things we did in the thing. And I'm going to show you a couple of examples in this area that we did. One is called the images to, I don't know whether you can see this clear or not. Okay, yeah. So this is like, for example, there's something called, if you take the human being, the gut system, the input-output system, take something and it comes out, okay, the input-output system. What you do is that they do what are known as endoscopies. Like if you have a lot of problems with like GERD, or you're having pain around here, they do this endoscope. But endoscope only can go until that level out there, okay? It cannot go any more than that. So then they do colonoscopy from the back. I don't know how many of you gotten this done, but if you're above 55, it's better to get one of these things done. So they do colonoscopy, goes from the back. Now, then what happens is, like the small intestine is very difficult for either of them to go. So we then, what is used is something called this capsule endoscopy. And the capsule endoscopy was actually first developed in Israel by a defense. I think you know those people. Yeah, you know them. Given imaging, you know them. Okay. So, and I don't know, for some reason it's not playing. Media not found, so it's somewhere on my Macintosh. I'm sorry, I converted from Macintosh to here. I should have checked. I didn't have time to check it. So anyway, that essentially what you do is that you take a capsule, and the capsule goes down, taking the images, and out comes the thing. Okay, so there's the capsule that you kind of ingest. Now, what this capsule kind of does is that it produces a lot of images, 8 hours of video it does. And then the doctor only is interested in some part of it. So what you do is that you can take the image of something, and then you do this segmentation of this image by talking to the expert doctors, and the machine learning system automatically kind of figures out this one. If a lot of doctors annotate this region of interest, and so on and so forth, and creates a feature network. And then once it does that, it maps onto an ontology. So now we have like neural networks kind of things doing these things, machine learning, and then you can map into an ontology. And the ontology will kind of, so if you look at it carefully, the features here, let me see the next slide. Yeah, if you look at these features here, these features indicate Crohn's disease, And Crohn's disease is really some kind of an idiopathic inflammatory bowel disease. And there is also this ulcerative colitis. It's also idiopathic inflammatory bowel disease. So you create these ontologies and you have this kind of a, again, this will segue into my third wave kind of thing. So people are really at the first wave, second wave really with the neural networks and imaging kind of. There's an excellent book by a guy named Gary Marcus. We'll come to that later on. And then there is this whole notion that is at the, and in this case, we are talking at the individual level, at the organ level. So you're now taking the organs and you're diagnosing problems. Then you have at the cellular level. So what we do is that we do a lot of work with our biology people. And in this case, they take the cells, stem cells, and they grow them in this petri dishes. And the stem cells are growing in the petri dish. So what we do is that we track the stem cells longitudinally over time, and at the same time taking images of that. And not all colonies of the stem cells are good, and only some colonies are going to be good. So we can determine which colonies are good. So we do an interaction between the biologists and the computer scientists, and using some machine learning techniques, we develop very robust, that's why we call trustworthy things, very robust system architecture we have developed so that you can essentially say that these stem cells are going to be good or bad. I got about 15 minutes to think, but I'm just gonna go a little bit faster around here. And this is important thing for me. And one of the projects that we worked on is called age-related macular degeneration. And the global cost is about $343 billion. And the problem here is that people who have this macular degeneration, their vision is, central vision is blurred because on the macula, you have some degeneration. So they can only have a peripheral vision. Now, what you can do with this stem cell therapy is that you can take the stem cells and grow them in this petri dishes over the time. And then it takes about 6 or 9 months to do. And then you can figure out which are the good stem cells. And then you can implant that good stem cells in the eye, and you will be macular degeneration will go away in a sense that you can manage it. And the reason why this is important is that because I have the gene that can cause macular degeneration. And people ask me, are we worried? I said, no, because my guys have already solved the problem. So why should I be worried? So I can get the right stem cells thing and implant it when it comes into picture. Okay? So that's one of the things that we're doing. Okay. So we do the quality assurance of that. And I'm going to kind of skip the things except that we have done using this. We have this entire architecture. And if you want more information about this, Peter Bacci, I don't know whether you know Regina Bacci or not. She's a famous robotics engineer. Her son works on this thing, and he developed a super duper system to do these kinds of things. I mean, this thing is really fabulous in terms of what it does. Yeah. And then, sometimes what happens, again, this is a big problem, which you should be also interested is that when people talk about data, many times it's not the big data that is a problem, it's sparse data that's a problem, especially in the medical field. So what do you do with sparse data? So you have to use just generative neurognans or something like that to create your data for you so that can feed into the system. Okay, so we kind of do those kinds of things. And here is a project which again Peter did in terms of generating the rules from neural networks. Neural networks, it's an input-output system. No explanation. And why did it say this thing? Why did it say it's a cat versus a dog? I don't know. The system says that. So then he has developed something where you can develop this actually rules. I don't want to go into too much in there in terms of using some signals. Some tech, they developed a way where you can develop this rules which says that if C1, C2, C3, then there is something. So we can generate these rules automatically kind of thing. Then we evaluate various schemes. I'm going to skip this thing. And then what is known, and then these neural networks, one of the fundamental problems with these neural networks is they can be fooled in a sense, like, for example, here you have, you can generate massive amounts of data and determine whether it's a penguin or something like that, penguin or a guitar. But then what people can do is that they can tweak it a little bit and give some background noise. And when they do that, that system automatically goes haywire. Okay. So, and then what you can do with these neural networks, you can tweak it at the data level. You can tweak it at the model level. Many times what people do is that they get models from outside and they try to apply, the model has already been trained. And then they come and try to apply it in a different domain. But someone tweaks that model and you get all kinds of garbage. So this is the thing, like then these are called Trojans that can be introduced into the neural networks. So here is a thing where the panda, and someone introduced some background noise, and the system now predicts that as a gibbon instead of a panda. So that kind of thing. So now the thing is that the Trojans are introduced all the time. And this is a big problem also within this Trojans. And this is a thing called, so the Trojans are a big problem that we are, that are happening right now in the neural networks. And DARPA has a program, IARPA, in terms of Trojan detection. So you develop algorithms for Trojan detections. How good are they? And let me see if I have time. I'm not have time to do that. But then if you look at this book by Daniel Kahneman, there is something called thinking fast, thinking slow. So neural networks are really thinking fast. You look at it, like you see something there, it's a snake, I immediately react to it. But then I look at it and say, yeah, it's a coiled thing. It may not be a snake. It may be some rope coiled in there. Yeah, that is thinking slow. So I can do my knowledge structures. A snake does something, it wriggles around. It's could bite you potentially, whatever it is. A rope is just standing still. So those are knowledge structures. So you need that too. So you need a combination of thinking fast and thinking slow. And Gary Marcus and Ernest Davis wrote this excellent book called Rebooting Ai, and it's a must reading for everyone, in my opinion. Okay. And there's a debate between the neural network guy, Oshua Bengio, who's I think from Israel, and he's maybe he's in Canada right now. And he and Gary Marcus had this nice debate. You should watch that on the TV. I have the YouTube thing. And actually, I wrote a book called Intelligent Systems for Engineering, which came out in 1997, where I really talk about neural networks and how neural networks can be combined with knowledge structures. The book was really knowledge-based expert systems. And then I wrote the book in 86, 87, and then I published in 1997. And then I suddenly said that, well, it's, there's something that neural networks and knowledge networks have worked together. And I introduced a chapter on neural networks suddenly into this book on knowledge-based systems. And I didn't want to call it knowledge-based systems because there were neural networks. So I call it intelligent systems for engineering. So then what you have is that now you have to combine both these things. Now we are in the third wave. This whole notion of knowledge networks are becoming very popular for those you are working in that area. So whenever you do any of these hard things, you come across this generic information modeling requirements around here. So there's a whole lot of requirements. I don't want to get into details of it, but one of the key thing is that you got to represent across scales. And OKNs kind of started out. In fact, NSF kind of funds this open knowledge networks. And what happened in this open knowledge network is that you want to have a standardized way to represent knowledge of the world. And that is open knowledge networks. So then there's a lot of representation schemes around here, from weak semantics to strong semantics, and things like your taxonomies and XML form at the weak semantics level, and things like model logic and first order logic fall at the strong semantics kind of level. So we are actually working on something called category theory. And what you can do with this category theory is that you can actually represent things which span across the things, from Newtonian dynamics to predicate calculus. All of them can be represented using category theory. And also, when we have done something else, which is called now you talk about this knowledge networks, the idea is that how can you create this terminology from literature? And if you're talking about diabetics literature, there's a lot of literature in there. Automatically, you want to create terminology. And so we developed a natural language system, which we got a patent for. And it was based on something a Sanskrit grammarian Panini did 3,000 years ago. He came up with this rule and rule-based technique. And we use that to actually generate terminologies from large literature. And also what we did was during COVID-19 time, there are thousands and thousands of articles were coming out. Now it's about 800,000 articles I saw there. And we could actually go and search those articles using our rule and rule-based system. We have developed a thing for that. Anyway, we don't want to go into details of that, except you can do taxonomies can be created like that automatically in diabetes patient, elderly, whatever it is, and all those things, because it does noun kind of combinations. And then it can, this is the COVID, you can go to Nist and look at our tool, the repository, and you can do all kinds of search techniques around this thing. So now here, what we have done is that now I'm talking about a lot of topics. I'm talking about knowledge-based systems, I'm talking about neural networks, I'm talking about natural language processing, all kinds of things within one framework. So in fact, I'm compressing 40 years of AI kind of history into 1 hour. And talking at a speed which is fairly high rate, I guess. So anyway, you can do, it will help you, just like the Google does search, this also does the search, but I think we believe it's more efficient in terms of for this particular domain problem. So what we are doing now is that we say, well, open knowledge networks are very good at certain things, like background knowledge, complex logic, you can do it, but they're not very good at unstructured data. unstructured data, whereas neural networks is very good at dealing with this unstructured data, like you can see in a lot of the works you're doing. So there's a thing called predictive coding, and what predictive coding does is that, again, don't want to go into details with that. It takes both the knowledge networks and neural networks, and it generates some kind of a probabilistic model. And there's a whole theory behind this predictive model, and that's the thing that we're working on. Now, one of the interesting things that you can do after all this is very successful, here is what is going to happen. Now, for those of you, like most of the time, you get New England Journal of Medicine. I don't know how many of you read that. And I kind of read the New England Journal of Medicine because my wife gets it. She's an internist. She doesn't read it, so I read it. Okay. So because she's too busy with treating the patients, where is the time to read this thing? So what happens is I look at she gets a whole lot of other magazines. And when you get some of these magazines, you see these things, read that. So this is a typical case history, a 50-year, I don't know how there's something. There's a 50-year-old male who comes with abdominal pain, distension, absolute constipation, vomiting for so many days, past history of weaknesses, anorexia, and so on and so forth. And then if you read this very carefully, the previous investigations, remember the colonoscopy, I talked about it, and they used CT scan and so on. They are not suggestive of Crohn's disease, okay, with all these investigations. And finally, what happens is that the histopathical examination of so on and so forth, and then they came to a conclusion that diagnosis of Crohn's disease was made. I think. Now this happens, and then what is read this? You have to read this carefully because there are a number of things that are happening here. One of the images have to be interpreted out there. So you can use neural networks kind of things to interpret those images out there. Then you have a lot of complex symbolic structures out there, and the relationships between these various structures existed there. And the system now should be able to read this thing, should be able to interpret this thing, this textual data, and give you a interpretation of what this actually is. And now what the system does is once you have this thing, it learns from medical literature. You don't need to do anything. So anyway, in terms of the future, there are a lot of things here. And for those of you who are interested in strategic plans, there are a number of things which have come out. The National Artificial Intelligence Research and Development Strategic Plan. There was a 2019 report, and right now we are writing I participate in some of these things. And 2022 or 2023, there's another report which is going to come out, and you can see that. And these are the strategic plans that they had. In terms, for those of you in academics also, it's very important that you should look at it, because if you look at it, there are a number of strategies, making long-term investments in AI research, effective methods for human AI collaboration, safety, shared public data sets. Public data sets are very important. Measure and evaluate AI techniques, and all the things that I talked about, they're near. Actually, now there's a new one. We'll have another strategy, which is more important. It's expanding the partnerships beyond the United States to the world, because we are not the only people. Then there's a 20-year community roadmap for AI research in the US, which came out from CCC. And then there's also a very, very important, very nice document, and there are very nice figures around here. And they talk about various paths that one can take to reach your goals, and they have several recommendations. And any of you who are doing any research and are developing a strategic plan should read these kinds of documents. They're very useful, I think. And this Eric Topol is a guy who wrote this paper called High Performance Medicine: The Convergence of Human and AI. Very nice article that, again, is a must-read kind of thing. But there are other kinds of things like explanation-based learning, which DARPA has put in, because if you look carefully, the neural networks are not very good at explanation. They may be good at doing things, learning performance, but they're very bad at explainability. And there was a huge program there called the DARPA XI program. And if you Google, you can find information about that thing. So now the important thing right now is, can you trust Dr. AI? What do you do? So you have to have a trustworthy AI. Again, if you are interested, I did along with Vint Cerf, who actually is one of the fathers of internet. He and I did a symposium at AAAS, the American Association for the Advancement of Science, on this topic called, can you trust Dr. AI? Now, again, I don't want to go into details about what this thing is, but there is a URL there. If you click on that, you can get the video of this. It's a 1.5 hours or something like that on that. And Trojan AI talked about that. These are some of the things that we're doing, project detections. And the recent thing that we are embarking on, this thing called emotion recognition. Now, why is this important in the medical field? The emotion recognition is that I'm talking right now. Now, am I do I look angry or do I look happy? Do I look happy because it's the first talk I'm giving after 2 years? So the question is that now now assuming that there's a video there which is recording me, that can tell what my inside emotional feelings are. And why is this important? Because a lot of times when you're talking about telemedicine and things like that, you're looking at the patients through to the computer, to whatever audio, the video kind of thing. And this audio also, the person is talking, and they actually mean something else. They say, doctor, I have the stomach pain. We don't know whether the pain is excruciating pain, or they were just lying and all those things. So with emotion recognition, you can do those kinds of things. So anyway, we're doing some work in that area. There are different ways of doing this kind of thing. Right now, we're doing on speech recognition, but we want to extend that to other kinds of things. So, and the reason is that if you look at the doctor of the future kind of thing, with this smart healthcare things are going to happen, where you have convergence of basically IoT and social networks. I'm not going to go into detail. I'm going to skip all these things, but here is some things that you're going to that is going to happen. That your electronic health records, your genomic data is going into something called plus something called health persona. Health persona is thing which the data that are being gathered by your iPhone, Fitbit, and all kinds of things. The data is being gathered, and whatever you're doing, your physiological sensors, your fitness tracking sensors, all of them going to health persona. So once you have that, then you combine that with all this EHRs and genomic data, you've got a personal health record. And the reason why this is important of having genomic analysis is because people who have, a lot of people, if you have stroke or something like that, people give what is known as warfarin, but that's a blood thinner. But people who have a mutation, which is, there's something called plaque, there is a drug which they give for this thing, which is called plaque or something, plaquis or something like that. I don't know why it didn't come there. So that particular drug interacts, for people who have mutations on that particular mutation, it's useless. So no point giving the drug. That's why you need the genomic. Remember I talked about predictive kind of medicine. So this comes into the thing. So this is an example to see how it works. I don't want to go into details, except that someone has some kind of asthma, and here the PHR and all of things are there. And then there's an inference engine going on there, and the data is coming from the external world, the sensor data, and the person's PHR and the health person, all of them is here, and the person is running, and he's running on that particular road out there, and system there says that air quality level is low, is pretty bad, and the rule-based inference engine automatically tells the person that you're prone to asthma, so go somewhere else. So this is the kind of things that we're going to see right now, and these are called smart network systems. So you're going to see smart devices, smart networks. Everything is going to be smart. And now, in fact, if you go to play to public, what is it, the Publix or something like that, you also find smart water, by the way. So everything is becoming smart. So for this 21st century doctor to happen, you need all these technologies kind of thing, because you might imagine the emotion recognition, video feeding, all of them will have to come into this picture for this 21st century doctor to be realized. Okay, so I think anyway, this is I'm not going to skip all these things. And I gave this talk about 10 years ago in NIH when I told them what is going to happen in the future. That data, the smart healthcare, this is what you need, and what is going to happen, and it's happening right now. So I'm very happy about the fact that I talked about. Really, I think look the same. Okay. Yeah, this game. Yeah. So some numbers have changed. Yeah, right. But see, it's like interesting that all of you are looking at it, but he observed it. Okay. So something clicked out there. Okay. Anyway, so in terms of the summary, that as I said, metrology for AI and AI metrology is very important, and standards play a major role when you talk about interoperability of the systems. You need to test these algorithms so that to increase the trust in AI, and the learning programs will have to explain their reasoning, especially in the medical field. And we believe that public partnership, private partnership will help to accelerate the progress, and challenge problems will improve performance. There are a number of people who can be credited for my talk, and I actually gave them credit in my talk on that. And I would like to talk in memory. This is in remembrance of Professor Sargur Srihari, and for those of you who don't know about Sargur, and he's the one who actually developed the text recognition system for United States Post Office. So in the olden days, Sargur died
Buffalo?
Pardon?
He's Buffalo.
Yeah, Buffalo, Sonny Buffalo.
He interviewed me. He gave me a job, yeah.
So you know, nice person. So he did, pardon?
I didn't know he died.
Yeah, he got diagnosed on March 1st with glioblastoma, and March 8th there was no more. And yeah, he's a very nice person,
Brain cancer.
pioneering work in AI. So just
His
in
wife is still there.
Rohini, yeah. So very nice person, and this one. Okay, so that's what. And I went a little bit over. That's okay because I know I went kind of really fast to give you an overview of the what has happened in the last 40 years, and you know, you can take the slides, and if you want any specific thing, we can talk later. Okay, thank you.
So I'm working on the first way also of trying to explain the meaning of weights between neurons. Some of the systems are complex. Now that and we didn't get anywhere, somewhat a little bit with maybe 20 weights or maybe 50 weights. So now we have 80 billion.
Yeah.
How on earth can anyone believe?
Yeah, so that's actually what the DARPA XIA program is trying to do. So what you do is that you make some assumptions there. Okay, so actually I'm not an expert in this field, so I can't really say that I know how to do it. But you can see the thing that we did on this extracting rules, and that can be done by for some signals in there. For that kind of problem, we can do it, but we don't know we can do it for all the problems or not. So you can do for a certain kind of problems where you observe some outputs. You can tweak some weights in there and see what happens, and you can do that. But then you're talking about billions of parameters. It's still it's something which people are working on it. That's what the XI thing is, and I'm sure that there is in the literature. There's a lot of stuff on that.
It's true. We also work on some trustworthiness.
Yeah. Yeah.
It turns out that, for example, one of the projects I had was 200,000 matchshots. Race.
Yeah.
Turns out some of the features I identified was a dead fly in the background.
Yeah.
Of the wall of some of the shots. So my board, the color of it.
Yeah.
So something that you probably would agree is not a feature that we like.
Yeah.
But that's so basically if that fly isn't there, then that's not true.
Yeah.
So it's really tricky. And I don't know, if this goes into anything that is sensitive, something like you're diagnosed as a severe disease, and how do you explain high uncertainty?
Yeah. So actually, you brought a number of important points. That's why I talk about the neural networks and knowledge networks. So the advantage of having knowledge networks here is many times in a neural network may come up with a thing saying that it's a gibbon and not a panda. So, but then the knowledge network knows that, hey, in these situations, there only can be pandas and not gibbons. So that's why if you combine both these things, you can resolve that problem. But still, the problem of explanation in knowledge networks, it's easy because you're going through the network, and then you can always, it may not be easy in the sense like at least it's tractable, you can work on it. But on the neural networks, you have all these weights that are created, and this is what we kind of did. We kind of did some, as you can see around here, this particular thing, you take and see some of these network nodes may not be, they're not really inputting anything in there. So kind of remove that thing and then see how you can go. You can narrow it. But unfortunately, you can do this for small problems. But if you want to go for huge problems, I don't know how to do it. Anyway, we may have to see how it can be done. This is some Raman spectrum. So that is a classification based on that. Yeah.
Continuously over 40 years from our side, that means technology side, and all these things improving. We are getting some kind of help with all that. to the treatment side.
Mhm.
But what has changed over the treatment side? Nothing. Still the prescription of pharmaceutical companies develop one magic bullet, one prescription is one chemical. And you alluded the situation that, what you call is yoga and all this
Yeah.
time, that we're talking on mind.
Mind-body medicine.
And interaction. So nothing is happening from that end. Whatever we do from this end,
Mhm.
how that's going to help overall
Yeah.
system if there is no interaction, no acceptance. In you said a doctor spent 40 years in medical college, and then maybe another 4 years or more in the training process, but they even don't have 1 hour training in diet.
Yeah.
Is the diet has anything to do with healthcare? So this end, we are pushed. Because we are pushed from that end, we are developing.
Yeah.
But what is going on in that end?
Yeah.
Who is going to talk about that?
I agree. So there is what is happening is that in terms of certain types of care, we are making excellent progress. Okay, even surgeries and those kinds of things. But take for example, I talked about this gut system, and I don't know how many of you have this problem. So a large population, I think, has this problem with the gut. Okay, I talked about that Crohn's disease and things like that, but there's inflammatory kind of things. But you also have this irritable bowel syndrome. A lot of people have that. And it's very hard to diagnose that kind of thing. And depending, you go to a doctor and then see that particular thing happens for so many reasons. It may not only happen because of some malfunction in your pathological system, but it can also happen because of the food you're taking, and that reacts with that system. And it can also happen because of stress. A lot of times stress creates the irritable bowel syndrome. People don't realize that. That's why I said stress is important. Mind-body medicine can control the stress, then you can control that. So these things are, so medicine has a long way to go. And that's why I said for the future of the healthcare vision, you need to make progress in all those dimensions, not a single dimension. Just because I have a super duper medical device doesn't mean anything. Okay, but there's also the other dimensions, and food you mentioned is very important, food and nutrition for this whole thing. And Ramesh Jain actually has written a good survey of this thing on computing food, nutrition, and things. It came in the communications of the ACM. So that's
So I think the integration of two ends,
Yeah.
unless it comes together, I think we have done a lot of advancement from this end. Whatever we have done, that provides a lot of help.
yeah, and AI can play a role in these things. Not AI is not the panacea for this thing, but it can
How
help
do
in
we
this.
use AI
Yeah,
from that?
that's exactly, that's what the thing that we look
You
at.
know,
That's why, if you look very carefully in one of the slides that I had, the tsunami, the fourth wave, the fourth revolution.
lot of alternative medicine treatment people are seeking because the traditional treatment, so traditional, actually that's not traditional, that's the existing pharmaceutical company marketing tools.
And
That is what the standard, and that to change that, we have this alternative care system.
Yeah.
So is there a way that we can push from that
I mean,
as a machine learning system, where we take these alternative treatments, and try to compare with the so-called traditional system?
yeah,
Can we build from that?
you can, but it's a question of who is willing. It's who's gonna. This I don't know whether you heard that who's gonna bell the cat kind of thing. So who's gonna do it is a question. I mean, who's the bell the cat in this?
Who's going to fund?
Yeah, the funding is the funding has to come from NIH mostly, and that's a big organization. DARPA funds, a number of organizations.
Even entertain such a.
I hope so. That's what I've been.
I'm not sure they will be entertained.
No, your question is
Somebody
good.
like me talks like that, or anybody from this end.
I'm sure there must be programs. You got to go to the NIH, especially with this new organization called ARPA-H coming. They might entertain these kinds of things because they want to go from research to bedside kind of thing, whatever it is, translational medicine. And that's going to be very important thing. And if people do not recognize the, as I mentioned, the alternative medicines and mind-body medicine, things like that, it's medical costs are going to go up. And why do you think the medical costs are so expensive around here?
The question I had was on the intrigued by what your thoughts are on why meditation reduces the effectiveness of the disease.
Not effectiveness. What meditation does is it controls the. If you want, there's a nice book on this thing. The guy actually came up with a mechanism of why it happens. Why it happens is that in meditation, you have what is known as an abstract thought. So you are doing in the Transcendental Meditation, for example, you do what is known as a mantra. Now you might ask me why this guy can talk so authoritatively about this, because I've been practicing Transcendental Meditation for 40 years. So I can say a little bit about it. So what the Transcendental, this is the one which Beatles and those guys. So what it does is that when you're doing this meditation, the meditation produces these waves of certain frequency. And these waves of certain frequency actually react with the cells at the cellular level. And that changes the structure of how the cell interacts with other cells and things like that. So and that has been done, the research has been done on people putting these monitors on the brain and trying to get the waves. When you're in deep meditation, what is the wave that you get and things like that. And those waves have an effect on the cell at the cellular level. And when it affects the cellular level, it also affects the metabolism and all kinds of things. And that's the reason why meditation.
Interested in that today.
Yeah.
I will tell you something. I was in Sydney for a conference in 1960. University of Sydney and Jane was doing a research, and what they did is for old elderly people, they physical exercise. It has shown that it changes actually the brain structure and so on. So in parallel, what they did is mindfulness for a group of people and physical, going to the gym and physical activity. And they were doing fMRI of the brain of those people. What was the most surprising thing? Those people were not going to gym, doing just mindfulness about same amount of time, the same change in the brain.
Yeah. So, because the other thing that happens is that if you look carefully at if we take schizophrenia, for example, twins. So there'll be twins are identical DNA because they have to be, okay, same thing. But then one may get the schizophrenia and other may not get it, although there's a chance. Why? And the reason is there is what happens is the genes have to express themselves. Okay, there's something called epigenetics. So if the gene doesn't express itself, you don't get the disease. So what you can do is you can control the epigenetic part of it through this mindfulness. Okay, I'm sorry.
We have a couple of questions online.
Oh, okay.
So now was asking at what domains do summer interns work at NIST, and are there any specific projects assigned?
Yeah. So again, we have. I think tomorrow I'm going to meet with some of the students to talk about it. But anyway, I can give you. So the way Nist works is that we do have a program called the SURF SURF program, which I think you will be seeing when you were there. They were involved in that. Where you undergraduate students who come and work with us. I don't know the restriction now whether they have to be US citizens or not. At one time they're not, but now they may be. Who knows? So with that they can come and work with Nist for it's a number of projects that I talked about. And if you're interested in other projects, you can talk to me. And there's a whole lot of stuff going on in Nist. And Nist is like one of these places where tons and tons of things are happening, and it's always good. And again, for US citizens. We have after PhD, they can come with us and work at a postdoctoral level for 2 years, and they can write papers. There's a lot of it. Tomorrow I'll talk about some of the advantages.
And then on the Q&A,
Yeah.
where I'll ask, not the open, it's a lot of questions.
Oh. Yeah, that's a problem with the international students. Okay,
So there are ways of working with international students, but it's not direct way. Anything. It's one of these things. Pardon?
He's the PhD student.
But he will graduate in.
Oh yeah, there is we have a program for international people actually. The program is called Research Associate Program. And the way that this program works is, if you are an international student, or if you're from international country, not a Genomic student, if you're an international student, could be student also, but if you finished your PhD, the only problem with this particular thing is that you are given a J1 visa. So you should be ready for that. And we will provide the support and we can work on a project of interest to you. We have that. We do have that for international students. Whereas if you're an American citizen, it's a little bit different.
Well, what would be the best way to present you?
I think my email is there, right in the slides. It's just my last name, which is sriram@nist.gov. When in doubt, there's something called when in doubt sprout. So when in doubt, go to Google and search.
I can put it on the chat.
Yeah.
More questions? Okay,
Okay,
so
thank you.
much.